Great. Welcome to our next session on all things artificial intelligence, machine learning, and data science. So I'd like to introduce Rob Claxton. He's a senior manager at BT's Applied Research. He's had a very various career, if you will, inside of BT, including working on signaling systems as well as software development. And today he's going to talk to us about, are we nearly there yet? So when you're talking about models in the whole artificial intelligence and machine learning space, how good is good enough? And how do you know what good enough looks like before you even start the journey when it's all said and done? So on that note, I'll hand over to Rob. So Rob, over to you.
Okay, thanks, Mike. So good morning. Yes, the title of the talk is Are We Nearly There Yet? And this is really about how we can use processes like building baseline models and early characterization of the performance that we need in our models for them to be useful in the real world, so that we can go from the question that we typically ask when we're building machine learning models, which is how good is my model, to what I think is a much more interesting question, which is how good does it need to be in order to be useful in the real world. So I think the theme for today was all models are wrong, so I thought I'd start by just setting the context for this talk and just look a little bit about how we can go wrong. So I've got three sort of ideas here. So one is that we can dive into machine learning and we can solve the wrong problem. So quite often we tackle a problem in a particular way because we've got a data set that's available and it lends itself to a particular solution. But what we actually really want to do is step back and think, what are the different alternatives here? And is there a way that I can tackle this problem if I frame it differently that's actually maybe going to be easier and might lead to better outcomes in other ways, for example, a more robust solution or a more interpretable solution. We quite often, as data scientists, want to leap in and apply the latest, greatest technology, and we can end up in the situation of using a sledgehammer to crack a nut. And again, here, what we want to be doing is thinking, what is good enough? What is the right approach here that's going to give me, perhaps I follow the simplest model that works, rather than necessarily thinking I need to apply the most sophisticated technique that's available. And then the final one, which is really the crux of the talk today, which is I've characterized as, but it looked great in the lab. And this is really where we see very often we build models and we measure their performance and we see how good we were versus the last iteration. And then we're surprised when we go into the real world and it all falls apart, and that very high accuracy model that we had in the lab just doesn't seem to cut it in the real world. So what does this all look like? Just to give this some context, what does the process look like when we go through building machine learning models, and how can we adjust this to try and tackle some of those problems? So what I've got here is a workflow. This is just from a book, which is Deep Learning with R. This is obviously based on deep learning. And so this is a fairly simple but a kind of typical workflow. So if we look at this, we can start to think about how this helps us address some of those problems. So the first steps are around framing the problem, actually defining the problem and trying to characterize how we're going to measure that. So these are obviously critical in terms of making sure we tackle the right problem. So this is a good start. And if we can do that well, then we can start to go through some of the other steps and eventually arrive at the bit that we all want to do and that everybody enjoys, which is actually building the model and seeing how good we can get. And in this workflow, what we've got is the proposal that you first build a baseline model. So before you dive in and get carried away, you establish some sort of baseline. So what does that mean? What does that actually look like? So a baseline model in this context is going to be a simple model, perhaps a very naive model. It could be something that's based on non-machine learning techniques or some simplified machine learning techniques. In terms of non-machine learning, there's some examples there on the right from scikit-learn. These are dummy estimators, and you can see these are very sort of simple, in some cases trivial ways of doing, for example, classification or regression. But the idea is that these provide some kind of baseline, some reference for all of the work that's going to take place later. So rather than that being done in a kind of a free-form way, you've actually got some kind of benchmark to aim for. You've got to at least be able to do as good as the naive or the simple model to be within a chance of solving the problem. And sometimes these simple techniques can turn out to be actually really quite difficult to beat. And if that's the case, then that sort of begs the question, well, should I be using a complex machine learning approach in the first place if I can get a really good result with something much simpler? Do I actually need to go down that path, or can I take a much easier route? So that whole process can be useful just for having that test up front of, which route should I be taking? Is it sophisticated that I need, or something much simpler? And just going through the process can actually be very valuable in terms of debugging the whole model, your data workflow, and your model building workflow. So it's a good, healthy thing to have in the process. And the other thing that we can start to get some insight on with building baseline models is to this question of how much more effort is going to be justified in order to reach whatever performance is actually required from this model, starting from my benchmark. So this can give you a really good handle on, is this actually a problem that's going to be reasonable to solve, or are we going to end up expending vast amounts of effort and resources? But in order to answer that question, we need to actually know what we're shooting for. So that then poses the question, how good does the model actually have to be? So in order to look at that, what we propose, so building on your baseline model, is even before you've gone into the process of actually building and developing some machine learning and AI, it should be possible in many cases to do an upfront analysis of what the performance target for your model has to be. And critically here, what we're interested in is how good does that performance have to be in order to generate a real-world benefit. So just to make that concrete, I've got an example here that's based on churn prediction. So this is a sort of classic ML problem where an organization is trying to predict which of its customers might churn within some particular time frame, and then it might offer them an incentive in order to retain them as customers and not have to bear the cost of then finding new customers to replace them. So to then trying to do this upfront analysis, what we do in this case, we have to define some sort of cost function. So in this case, I've got a fairly simple function just for illustration today, but you can see essentially we're looking at, for our model, if we get the false negatives, they're going to be the customers that are going to churn that we failed to predict. So there's a big cost associated with losing those people. And the true positives and the false positives are the people that we're actually going to give incentives to. And so we can use the cost function to then assess the model performance. And so for a given model, what is the net benefit versus doing nothing? And I've got some examples here. In order to derive these charts at the bottom, we have to plug some parameters into the cost function, of course. So we'll put a cost to losing a customer. We'll put a cost to the retention of a customer. And then we can actually see, for different scenarios, what kind of performance is good enough and what doesn't cut it. And so in these charts, the shaded areas are where we've got a net positive benefit. So anything from blue to yellow in the shading is sort of break even up to sort of maximal benefit. And obviously we want to be in the top right of these charts. And here we're showing sensitivity and specificity of the model. And it's done for different levels of prevalence, i.e. different levels of churn within the population. And what's quite interesting is you can see that for plausible levels of churn, sort of typical levels of churn, the region where there's actually a benefit is quite narrow. And in reality, it would be much narrower. We've made some really generous assumptions here about the model scenario. So for example, we've said there's no cost to operating this model. And if we identify a churner, then and we offer them an incentive, then they'll definitely stay with us. And in reality, that's simply not true. So in the real world, these regions would be much tighter. So what we've got now is a much better handle before we've even begun thinking about what kind of model we should use, what sort of approach we should take, or anything like that. We've actually got something to shoot for. We've got some constraints around the problem. And the other thing we've got are some questions to ask and some knowledge gaps that we might want to spend time closing, again, before we proceed down the path of building the models. So the questions are things like, are the parameter choices I made here reasonable? Where did they come from? What happens if they change? How sensitive are we to those? Crucially, in this case, what's the relationship between the incentive that we offer people and the chance that we'll actually retain them as a customer? That's a complete unknown in this model. We've assumed that we get perfect retention, and again, that's just not plausible in the real world. So we've now got some things to go after and some gaps to close. And all of this is going to help us, if we do decide to proceed, to hopefully build a model that actually delivers a benefit, and we can manage in life to make sure it continues to do that. So if you think back to that workflow that we started with, here's a slightly modified version of that now, based on introducing the ideas of baselines and this upfront assessment. So very briefly, we define our problem, we try and characterize what success means, how we measure that. Then we introduce this step of how good does the model need to be? So this is before we've even begun the model, characterize the performance that we need, and understand the assumptions and the sensitivities that rests on. And then we can flow into the next step, which is build our model baseline, give ourselves a reference point, something to shoot for. And then finally, we're ready to go and build the model. And now we're in a position to actually ask the question, are we nearly there yet? Because we've actually got some constraints around the required performance, and we've got a known benchmark to work from. And I think that gives us a much more stable way of proceeding. And then finally, if we're successful, we go into production, and we can deploy the model, and we've got the basis for making sure that it continues to work successfully. And as we're going through this process, we're learning all the time, and we want to capture that learning and flow that and transmit that into the future so that we can manage this model safely. The way we do that is by capturing all of that knowledge in what we call a data sheet, a model data sheet. What's that? Well, it does lots of things. It's intended as a means of capturing all the key facts about a model, how it got built, what it's used for, what its sensitivities are. But crucially, this is where we can lodge information about how to manage that model in life so it continues to deliver the expected benefits. Here's an example of a model data sheet. This is from Google. They call them model cards. And so you can see, I've put some links in there. You can see the kind of material that's included in their data sheets. And this is what it looks like when we bring it all together end to end. So we start with step one, where we're upfront, we're doing our model performance assessment. That's helping us to generate criteria that we're going to use later in production to actually manage this model, make sure it's operating safely. That all gets captured together with things that we learn in the model development process and the sensitivities and assumptions that came from that original upfront assessment. And that goes into the model data sheet, and specifically what I've called a model contract. And this is the thing that defines the safe operating or the required operating area for that model. And then finally, that can all be used to hopefully generate either manually or automatically software components that are actually going to manage that model in life and make sure it continues to deliver a benefit. So that's the end of the presentation, and hopefully I've persuaded you that there are some simple steps we can take to make sure that our models really are fit for purpose in production and they stay so.
Great, Rob. Thank you very much. It's really fascinating about starting this whole journey with what does good look like in the first place before we actually start the work at the end of the day, instead of just plowing into a whole range of data and so forth. So, Rob, thank you very much for that. Once again, some really fantastic insights in terms of methodologies to make sure you can actually validate your data.